Rules for obtaining images formed by convex lens. This is rule number 1. First we need to draw the lens. We first draw a straight line and then a perpendicular. After you draw the perpendicular, from the point here at the optical center, which is here, you take 4 centimeters and mark here, mark this point, call it F, and then take another 4 centimeters and mark this point here and call this 2F. So you can extend this line further. Do the similar on the other side. So from the optical center, which is the center of the lens, mark 1 here, 4 centimeters, and then mark again another 4 centimeters at this point. You're going to call this as 2F, but this is F, and this is 2F. F1 to F1, F2 to F2. Then with free hand you can just draw a thin lens. This is your first step. Now the first rule is we take a ray of light which is parallel to the principal axis of a convex lens. So here now I'm taking a ray of light that is parallel to the principal axis. This ray, after refraction, will pass through the focus. This is the refracted ray. It will pass through the focus. So this is the first rule, and here they have drawn the rule. Here I've drawn it again. This is a ray that is parallel. After refraction, it always will pass through the focus. Even if you take a ray, say down here, a ray that is parallel, after refraction it will pass through the focus on the other side. This is rule number 1. Now for the second, you draw the 2 perpendicular lines and you mark your F1 here, and here at 4 centimeters 2 F1. So, or you can even write this as F2 and this is 2 F2. The same thing on the other side. Here you mark 2, so this is F2 F1 2 F1. Then you draw the lens. The central position is called the optical center. Now next we are going to take a ray of light passing through the optical center, goes straight after refraction. So here the ray of light is passing through the optical center. Here it will go straight down undeviated. So here this is rule number 2. Like here we have drawn, this is the optical center, and a ray of light comes parallel, and this not parallel, comes through the optical center, it will go undeviated. So remember, this is rule 2. Again, you draw a line and draw a perpendicular. From this perpendicular you need to mark the focus. So at 4 centimeters you mark one, at 8 you mark the other. So we mark this as F2 and this is 2F2. You can extend this further and do the same on the other side. So you will now mark here F1 and 2F2. So this is F1 and 2F2. Now draw your lens. Draw a thin lens. This is your convex lens. This is the optical center, the central point. Now in this we are going to take a ray of light passing through the focus of the convex. So a ray of light that passes like through the focus, that goes through the focus like this, will go after refraction, it will go parallel. Let's take another example. You have another ray of light here coming through the focus. After refraction, it will go parallel. A ray coming through the focus, after refraction goes parallel to the principal axis. And here again we have a picture here. This is an optical center. This is a ray that is coming through the focus. It then goes parallel to the principal axis. Here through the focus goes parallel to the principal axis. This is rule number 3. So let's just summarize the rules. This was parallel to principal axis. This next one was a ray that was through the optical center. And this was the ray that came through the focus. Let's see how they behave. This one, that is first one, parallel to the principal axis, after refraction will pass through the focus. So this one passes through the focus after refraction. The one that is passing through the optical center goes undeviated. And the one that comes through the principal focus after refraction goes parallel. So this goes parallel to principal focus. Now using these 3 rules, that was rule 1, rule 2 and rule 3, let's go ahead and draw the ray diagrams. So we take up the next case where the object is beyond 2f. So we'll keep the object here beyond 2f. And from here we take 2 rays. One ray will take parallel to the principal axis and the other ray will take through this optical center. So here is the next ray which is passing through the optical center. Now the ray that is parallel to the principal axis, you know, after a refraction it will pass through the focus, and the one that is through the optical center will go undeviated. Now they will meet at this point. So here is the image. So this is the image now here. So if I put A, B, the image of A is from here, A dash, B dash. So if I were to tell you what is the nature of the image, you will say, 1, it is diminished. You can see in the picture that the image is diminished. It is real because the real rays actually meet, and it is formed between F and 2F on the other side of the lens. We'll go to this again. Here I have the object, and from the object I get 2 rays. One that is parallel goes through the focus, and I'll put this in another color, that is passing through the optical center will go undeviated. The rays meet here. This is the image. It is real, inverted and diminished. Another point I need to write is inverted. All real images are inverted. This is when the object is beyond 2f. So you draw the 2 perpendiculars and then you mark your f and 2f, and also on the other side you mark f and 2f equidistant. So here you have your f2, 2f2, f1, 2f1, and then you draw a lens. Now in this case we are going to keep the object at infinity. Infinity means it's just very far away. And two rays again, one that is so when the object is kept infinity, in fact I must not draw the object because it's very far away. The rays come parallel, and so when the rays come parallel, when an object is kept at infinity, we consider the rays to come parallel, and the rays that come parallel, you know, they all converge at the focus. So the image is now formed here at the focus. And if you were to know note down the nature of the image, you will say it is real because the rays actually meet after reflection. Here, real, because it's real, it is inverted. Highly diminished, see, it's just a dot. And it is formed on at the focus. On the other side of the lens. So this was an object kept at infinity, like that the sun or a faraway object. So you need to draw these 4 points, 2f1, this is 2f1, f1, f2, 2f2 equidistant. You can keep 4 centimeters, and then you draw the ray, draw the lens here. And now the object, we are going to keep it at 2f. So here is the object at 2f. From here we'll have two rays. One ray that comes parallel and the other one that goes through the optical center. Now the ray that goes parallel, after refraction, we know passes through the focus, so it will now pass through the focus. And the one that goes to the optical center will go undeviated. Will go along like this, undeviated. So here it's going undeviated, and if you see, they are going to meet, they meet somewhere here. So here is your image. This is your image formed at 2f2. So you have AB is the object and the image is A dash B dash. This is your image. So if you were to write the nature of the image, we will first say it is real because the rays actually meet, and because it is real, it is inverted. The size is the same. If you compare the size, it is same size as object, and it is formed on the other side. It is formed at 2f2 on the other side of the lens. Here again we have, see, this is the object. From here we have two rays, one going parallel which goes through the focus, and that one goes through the optical center, goes undeviated, and they both meet at this point. Here is the image formed at 2f. Nature of the image, real, inverted, same size as that of the object. This was case 3. So draw a line and mark these 5 points, and then you draw for the lens. You draw this perpendicular here and you complete your lens. You will mark this point as 2f1, f1, f2, 2, f2. Now we are going to keep our object between f and 2f. So f and 2f here, we're going to keep it in between. This is the object, say AB, and we'll see where the image is formed. We take two rays, one that is parallel to the principal axis and the other one that passes through the optical center. So the one that is parallel, you know, after a refraction will go through the focus, and the one that is going to the optical center goes undeviated, so it will go undeviated. So this is the one that goes parallel, passes through the focus, and here goes undeviated. If you see, the rays are meeting at this point, and the object is now here. This would be A dash and this would be B dash. This is the not object, this is the image. Now to write the characteristics of this image, the image is real because the rays actually meet. It is inverted, you can see it is inverted. It is magnified. Compare the object and the image and see, it is magnified. And it is formed beyond 2f on other side. Of the lens. So let's draw this again here. Here was the object, and from the object we had two rays coming, one parallel, it went through the focus, and the other one went through the optical center, and here is your image formed. Real, inverted, magnified beyond 2f. This was case 4. So you mark these points, then you draw your lens. Remember, the point should be equidistant. Now the next case, we are going to keep it at the focus. So here we have 2 f1, f1, f2, 2f2, all equidistant, and we will keep it now at the focus. Here we have two rays, one going parallel and the other one passing through the optical center. The one that is going parallel after refraction will pass through the focus, and the one to the optical center also will go undeviated. Now if you see, these rays do not meet, they are parallel to each other. So we imagine that the image is formed at infinity, because the rays are not meeting. So if you were to find the nature of this image, it would be real, it would be inverted, it is formed at infinity and highly magnified. Here again we will mark, this is the image object kept at focus. We have two rays, one going parallel after refraction passes to the focus, and one through the optical center, and the rays are parallel, and because they are parallel, we say that the image is real, inverted, at infinity. It is parallel, the rays do not meet, so we assume they meet at infinity. The image is formed at infinity. So this was case 5. Again, this is the case 6. We mark these 4 points, then you draw the lens. Now the object is kept between optical center and focus. So we have 2 f1, f1, f2, 2 f2. So we will keep the object out here between the focus and optical center. Again, two rays, one parallel and one passing through optical center. The one that is parallel after refraction will go through the focus, and the one through the optical center will go undeviated. So this goes undeviated. If you see, the rays are diverging, so we produce them backwards. And as you produce them backwards, and you have the other ray here, which will now produce backwards, and they appear to come from this point. So the image will be here, but it will be a virtual image. It will appear to be here. So this is A and B, and this is the object. You will get here A dash, B dash, and this is the image. Now for the characteristics of this image, it is virtual because the rays do not actually meet, they appear to meet. We have to produce them backwards. It is erect. If you see, it is magnified. The image is much larger than the object and same side as the object. This is the case of a magnifying glass. So if you remember, the special case is the case of a magnifying glass. Here remember, the object was kept between optical center and the focus. Here is where we use it. Have you seen, this is the magnifying, this is the convex lens, and whatever is within the lens, it gets magnified. This region has got magnified. So this is an example of magnifying glass. Convex lens can be used as a magnifying glass because it gives magnified image. Here we got a magnified image of the comb, this area.